Hello and welcome to another video on orbital mechanics. We are still following through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and we're up to problem 1.11, which is part of section 1.6. We're just going to go through a little bit of the theory in the book first before we get onto problem 1.11 because it's getting a little bit more complicated. I think it's worth going over it. So this is on the topic of time derivatives of moving vectors. And what this piece, if you read the book, you should get some context. What it's trying to say is that this vector A is rotating about an axis, and the magnitude of A is not changing, but the direction is. So this is a triangle here just sitting on this plane, and it's rotating up into this position here, an amount by theta, and the angle of this A to the axis of rotation is phi. And so in the book it gives this equation here, and these equations, I'm going to go over them. This line here, B, is actually this section here because of the sine equals opposite over the hypotenuse. So that's the magnitude of A times the sine of phi, and then that is times by the angle here, and then multiplied by n, and n is also in this direction here, and so that is multiplied by that, and that is going out of the page. And so the size of this vector is proportional to the length of B and to the amount of angle in theta. And we also know that d theta equals the angular velocity times the change in time. So that's the integral. And we also know that the angular acceleration is the derivative of the angular velocity. So we can put those things into there to get rid of this. And so down here we have dA equals magnitude of A times sine phi times the magnitude of the angular velocity times the change in time times the unit vector in the direction that we want. And then simplified, he just reorganized here and simplified, because I don't like to use those pipes. If I don't have a line above it, then that's the magnitude. If there's a line above it, then it's the vector. That's a bit easier to read. And then we also can say that, well, we know that this vector here is actually, so if we take the cross product of this and this, we get a vector coming out of the page. So, and that is effectively the same as that, right? Because that's got an order of magnitude, and that's got an order of magnitude, and it's generating this vector that is well, this is 90 degrees to this because it's rotating around it. It has to be 90 degrees, so it is effectively, doesn't matter where it's coming from, the vector is going to be correct at that position. And so we can take that there and we can plug that into here, and we just get dA equals angular velocity cross product A dt, and then we move the dt over here to get the derivative of the vector A equals angular velocity cross product with A. So it kind of makes sense that this is what it is, because we're basically saying as this grows, the change in angular velocity is going to result in more change to this vector over time. And the angular velocity is you know, the rate of change, so that's fine. Like, once we have this component here, it also goes on to give examples of derivatives of this. So the second derivative of this is using the product rule. So you can look the product rule up, but you know, you can see that's what it is there. From this becomes this, which then dW by dt is angular acceleration, and we know dA by dt is this. So it just kind of recursively unfolds. And then there's another part in the book that does the third derivative. So if we look here, d3a dt cubed is, we'll split it into two parts, into the addition. And then this bit is straightforward enough. That's just more product rule. This one is like product, well, it's just like recursively doing the product rule. So we split it into two bits. We do the product rule, and we just keep doing the product rule, and it just keeps unfolding. And then once we've done the product rule as much as we can, we aggregate all the terms together. And that's the final equation. Now, problem 1.111 states that W is 2k, angular velocity is 2k, angular acceleration is minus 5k, and the derivative of angular acceleration is 3k. And it says F in the book, I've just changed it to A, but A is 15I plus 10j, and the derivative, the third derivative of the force A equals question mark. So that's what we're trying to find, and that's what this is here. So when we input all those values, I didn't do this by hand, I did this in MATLAB, and the MATLAB script is included in the description. You get 500i plus 225j. So that is that. Hope that was understandable. Thank you. Bye.